Okay, so what we need in order to graph our exponential function here is a set of key points. And the key points depend on what the base function is that we started with. And so we know our base function is y equals 2 to the exponent x. So let's start by writing our x values. And then we can solve for our corresponding y values. So remember, when you're looking at graphing, you want to choose a value of x to the left of the y-axis, then a value on the y-axis, and then a point to the right of the y-axis. So -1, 0, and 1 are typically what we use. Now, because the base function is 2 to the exponent x, I'm going to look for 2 to the exponent -1 for the first one. So x is -1. I'm looking at 2 to the exponent -1. Then 2 to the exponent 0, and then 2 to the exponent 1. So we're just applying the value of x that we have to the base function. And so I get 2 to the exponent -1 is the same as 1 over 2 to the exponent +1. So the reciprocal of the base to a positive exponent. And so that gives me a half, which I can write as 0.5. And then 2 to the exponent 0, we know anything to the exponent 0 is equal to 1. And 2 to the exponent 1, we know that an exponent of 1 on any base gives you the base that you started with. And so we can transform these points to a new set of points. And if we look at our horizontal transformations, look at the exponent part. That's where all your horizontal transformations are anyway. And so I have a horizontal compression by a factor of 1/2, followed by a horizontal shift to the left 3. So this would be 1/2 x minus 3. So compression by a factor of 1/2 and then shift to the left 3. In terms of my y values, I have a vertical stretch by a factor of 3 and then a shift down 4 units. So this would be 3y minus 4. And if I solve for the values of x and y, you'll notice that those are going to be my key points. Now, I wanted to highlight this 2 that was here. And oftentimes students have a misconception thinking that that 2, which is the base of the exponent, is also a transformation, but it's not. What this 2 represents is the original base function that we started with. So please remember to keep that in mind. Let's find our x and y values of our transformed graph. So this would be -3.5, -3, and -2.5. Okay, and for our y values, 3 times 0.5 is 1.5, and -4 is -2.5. 3 minus 4 is -1, and 6 minus 4 is 2. So we're going to plot our points on a graph. Remember that there's a horizontal asymptote at y equals -4. You'll notice that all your y values are higher than that, which means the graph is above the asymptote. And that makes sense because the only way that a graph can be below the asymptote is if the graph had a vertical reflection along the x-axis. So we can graph this very quickly. Okay, so there's my x-axis, there's my y-axis. And horizontally, I need to make sure I go up to about -4. And vertically, I need to make sure that I go at least down to -4 because that's where my asymptote is. So 1, 2, 3, 4. And 1, 2. And I'm going to start by drawing the asymptote because that's going to create a restriction in my graph. So I know that the graph can't go past the asymptote. And so I'm going to plot the points at -3.5 and -2.5. Then I have a point at -3 and -1. And I have a point at -2.5 and +2. So you'll notice that the point that's closest to the asymptote is indicating that the graph is going to get closer to the asymptote from there. And the point that's farthest away from the asymptote indicates that the graph is going to continue in that direction and go towards positive infinity. And so here's a graph of y equals 3, 2 to the exponent 2x plus 6, and then -4.